On 5, 3, 2, 1. Hi, guys. Hi, guys. It's nice to see you again. I'm here with Dr. Jose Gonzalez-Rodriguez from University of Lincoln. First, I would like to say thank you, Dr. Jose, for accepting our invitation, quickly accept our invitation, by the way, and for being here to be our guest honor in this first event of the post-graduation of our post-graduation program, chemistry of our university, for Federal University of Paraíba. We are celebrating the 36th, I believe, anniversary of our program.
Congratulations.
Thank you. And we are happy to have you here for your, I believe the Professor Liliana had an introduction about yourself, but I have some words in English for the worldwide audience to know a little about you. Okay, so I can tell a little words about you, and after you can start your presentation.
Yeah, thank you.
Professor Dr. Gonzalez-Rodriguez holds both degrees in chemistry and biochemistry from University of Cordoba, and a master's degree in environmental science from Polytechnic University of Madrid, PhD from University of Cordoba also in analytical chemistry, and has developed research in this area for more than 19 years. And Dr. Gonzalez has published 6-7 publications, 40 communications to Congress up to date, and has attracted funds over £3.5 million, wow, to date over this period. He's currently the program leader of the Masters in Forensic Science of the University of Lincoln, and has also refereed more than 200 papers for international journals, and has acted as evaluator and reviewer for different national and research international bodies, including the Portuguese Research Agency, the Academy of Finland, the European Commission, in programs such as Security Society's FP7, the Horizon 2020, and the Marie Curie program. Recent public engagement includes 2 written evidence to the UK Parliament in COVID-19, I believe. Yep. He's a member of several professional bodies such as the Royal Society of Chemistry, American Chemical Society, International Society of Electrochemistry, and Society of Forensic Science of the UK. Currently, he's supervisor for 4 PhD students and 2 master by research. So today, Professor Jose is gonna talk about us of experience in forensic analysis, most specifically in explosive and explosives taggants. So Professor Jose, thank you again. And I'm gonna show you a presentation, and you feel free to talk to us. Thank you, Jose.
Thank you, Sheldon. Okay, well, first of all, I would like to thank the University of Paraíba for inviting me. I mean, Dr. Sheldon for inviting me, and you guys, because you're going to actually listen to my blah and my talk. So I hope it's going to be entertaining and educational, and at the end, you're going to know a little bit more about the world of explosives and explosive taggants. So, I mean, when we talk about explosives, you know what explosive substance is. It's a mixture that undergoes a chemical oxidation and rapidly basically release energy. The energy is in the form of heat, light, sound, and a wave pressure, or pressure wave, sorry. Yeah. So, I mean, if we are going through a formal classification of explosives, we can basically classify them in high or low order. And that is basically defined by whether they actually are going to deflagrate or they are going to detonate. And what difference is actually one or the other. Basically, that is determined by the whether they break the speed of sound or they don't break the speed of sound. Basically, that pressure wave is faster than the speed of sound or not. So important thing the thing that is actually mattering the most when you actually looking at the release of energy is that release of energy is fast. I mean, just to give you an example, I mean, you have black powder. I mean, if you look at black powder, that's going to, everybody understand that that's basically an explosive. It's going to detonate and it's going to produce energy. But actually, if you look at the Snickers, I mean, the chocolate bar, you basically get on the screen, you have a comparison between black powder and the chocolate bar. So if you actually look that 1.5 grams of black powder is going to release 3.2 kilojoules of energy. And you look at that, the chocolate bar is going to release 2,137 kilojoules per 100 grams. I mean, if you do just the comparison per gram, you can see actually that if you look at a gram of chocolate and a gram of black powder, the chocolate contains more energy. And then, but nobody actually dies from an explosion from a chocolate bar. So why is that? It's because the energy that you release with chocolate is very slow. You cannot basically make it work fast. However, with black powder, when you have the adequate oxidant, it's going to release that energy very fast. And that is the difference. So it's not the amount of energy you can store in the molecule, it's actually how fast the energy can be released. So actually, not now, but then when you actually look at this, you can go to the YouTube. We produced a video years ago where you can actually go through the calculations if you're interested in how much energy is released by explosives. So basically, coming back to the original, non-discrimination classification of explosive, we said basically low order explosives are those who actually deflagrate at a rate of 343 meters per second, speed of sound. And they are the typical ones you may know, basically powders, gunpowder. You can basically get that with basically that's the organic fuel with sulfur charcoal. And then you add on an inorganic oxidizer, which is basically could be chlorates, perchlorates, nitrates, those sort of molecules that are going to supply with the oxygen needed for the explosion. So, and you had the high order explosive. And then when you come to these high order explosives, you have two types again. You have those that are classified into primary and secondary. And the primary are the ones you have on the screen. You basically, they can be mercury fulminate, lead acid, lead estibnate. They are basically called like special purpose. They are actually quite sensitive to stimuli, energy like heat, friction, electricity. They actually blow up quite quickly if you actually add energy. And then you have the secondary explosives, and those secondary explosives are less sensitive. They are the ones that we know well. I mean, TNT, everybody knows that because it's the typical explosive that actually you find in many military applications. And then you have other that they may be less known or well known for the non-specialists, basically like HMX, PTN, RDX. I mean, those are high explosives that actually are going to release a lot of energy. But the key thing here is that when you're looking at how explosives work, I mean, if you have three possible scenarios with explosives here. You can see that on the screen. We are going to talk about what we call in the explosive world, like the explosive train, where you have an ignition source. That ignition source is going to be heat, pressure, electric current, shock, friction. That is the initial energy you're going to give to a primer. And that primer is going to be those primary explosives that we were talking about before. Mercury fulminate, they are going to actually produce a small explosion. That explosion is going to go sometimes through a detonating cord. usually another explosive, high explosive, PETN, and then you have another secondary explosive that is going to produce, it's like the main charge that is going to produce the Big Bang. And then, again, you can see on the screen that there are different ways you can actually produce this explosive train. You can have a propellant. Sometimes you can add black powder to actually make it more fast. Well, the reaction is going to go faster. You can ask boosters that is going to actually increase the energy. I mean, again, there are different combinations. I don't want to go too heavy on this, but then this is going to be necessary to produce an explosion. I mean, you're going to see that very clearly later when I show you some pictures. So an example of a very common explosive that actually is available for mining. Basically, you can find this explosive in quarries, and it's actually relatively easy to produce. I mean, some terrorists have been using this one because it's actually quite stable. It's ANFO, ammonium nitrate fuel oil. I mean, probably you've heard in the news that sometimes basically there are big explosions in farms. I mean, probably the best known explosion down to ANFO is actually in Lebanon a couple of years back, because it was a massive warehouse full of ammonium nitrate, and actually it overheated and then produced a massive explosion. It's actually, ammonium nitrate contains a lot of energy, and you only need 95% of ammonium nitrate, 5% fuel oil. That's a little bit of organic material you add, and that's going to actually trigger everything. I mean, some people have used this explosive in the 20th century. I mean, a little bit basically back in 1995, there was a very well-known attack on Oklahoma, and then 168 people died, and that was basically 2.2 tons of ANFO were used to actually demolish the whole building, and then they killed loads of people, as we said. So what is the problem with this explosive? You need to have a lot of energy to actually detonate. It's quite stable, and that's why it's used in mining. So actually in Brazil, I mean, you are very well-known miners, and then probably many people, when they actually using explosives in mines, basically they will be using ANFO, because as we said, it's quite stable. You will need a detonating core to actually explode it, but it's quite easy to manufacture, but also quite easy to actually store safely. So you see, for example, this is an example where you have a failed terrorist attack. So someone was actually planting a bomb on the roadside, and then you can see the hole there, and then you can see the cable. So that was detonated remotely with a detonator, basically from maybe 100 meters away or something like that. And then you can see was a butane, a gas cylinder that was emptied, and then they filled it up with that powder that you can see with the black bits. That is actually ANFO. And then they were using detonating cords that you can see on screen. So actually they are military grade ones. So actually you need to have access to those in order to actually detonate ANFO. But in this case, obviously the terrorists basically managed to get it. And I mean, the luck escape for the people in this road is that actually it failed. So actually the police and the military could actually recover the whole explosive and analyze it later. So here basically is us. So basically Dr. Prael is actually, she was one of my PhD students years ago, and then she's basically a forensic specialist in the Thai service, in the forensics service in Bangkok. And then you see here basically how we prepared a bomb. So actually you can see that Dr. Prael, basically, she's actually filling up the tube. And the tube is basically a pipe. It's basically a pipe you use for transporting water. And then we actually transform the pipe into a bomb with a detonating cord. We put it on a metal plate to avoid any craters. And then obviously we prepare our scenario so we could actually capture the debris. So basically you can see the different barrels, like the blue barrels with the little trays, aluminum trays, so we could actually capture any debris coming from the explosion. So please, Sherlan, can you show what we did?
Stand by for firing. Firing now.
Wow. That was good.
Okay, it didn't show well. Hello? Okay. So yeah, you didn't see the explosion there. Actually, that was very you basically heard the explosion, but you didn't see it. So that's okay.
Sure. We could can show again?
Yeah, we can try. Yeah, should we try again?
Stand by for firing. Firing now.
Wow.
Okay, now you saw the explosion. Yeah.
Yeah. Wow.
So yeah, that was basically me recording with my mobile phone 100 meters away in this safety perimeter. So yeah, yeah, that basically brings me to common homemade explosives for improvised explosive devices, basically IEDs. So if you look at unfortunately the world we live in, I mean there was a document produced by Action on Armed Violence, and that was basically 2017. It's like 5 years ago, and there were basically around 21 countries suffered explosive actions. And then 56% of the dead people basically were caused by improvised explosive devices. So actually, and then if you look at the number of dead people because of violent action, basically explosives is half of the deaths. So basically, when you talk about people trying to kill other people, explosives come into the action, sadly. So what we need to do? I mean, ideally, we need to stop terrorists or organized crimes from using explosives. Sometimes that's not possible. And then if we cannot avoid the tragedy, what we can try to do is track the perpetrators, and then if we get evidence, bring them to justice. And that's the best we can do, really. I mean, and I'll show you some examples later how the British police is actually doing that. So we have two scenarios when we are dealing with explosives. We have people, you can fabricate explosives. It's not complicated. But yeah, the problem is the homemade explosives and the homemade detonators are very, very unstable. So actually, I mean, you can go on YouTube and you can find recipes. Please do not do that, because there are many people that claim that you can manufacture explosives with household products. That's true. Yeah, you can. What's the problem? They're impure. And then impurities basically can catalyze reactions. You will see later how I'm going to present some information about how catalysis can actually produce reactions that we are not expecting. So actually, when you have a very impure sample or products, you could actually risk yourself. So don't do it. It's not safe. Leave it to professionals to do. The other thing is you can manufacture the more stable ones, and that's what professionals do in companies and yeah, explosive production companies. But then the detonation requires a more sophisticated detonator. They are military detonator that you only find when you are dealing with professionals. So actually, again, that is I mean, unfortunately, that's why some organized gangs tries to steal military equipment and military detonators, because then they can actually manufacture these and then use it for the wrong purposes. So what we need to actually look at? I mean, we're looking at the explosive. The explosive molecule is very well known. I mean, we're talking about TATP. This basically is a molecule. But explosive is not just the molecule. The explosive is a very, very sophisticated mixture. It's a complex mixture where you add other substances. You basically can add, for example, the ethylene glycol. You have the ethylene glycol dinitrate, the EGDN, is actually added to nitroglycerin to reduce the freezing temperature. You have plasticizers to actually make them like the plastic explosive to make it like flexible. There are many different type of additives you add to explosives to actually change the properties of the explosive. And obviously that is being done after very basically strict safety measures, and actually after years and years of research. So actually, again, when you add in something to explosive, it needs to be thoroughly checked, because you will see later when I'm talking about tagans how things may be or not may be added. So we need to understand the mixture of these additives. Why? Because when we understand the mixture, you can see what's in there basically added to make the explosive safer, more efficient, and what is there that we don't know what is there for. And then you will see later that when you actually look at compounds in explosives, sometimes you find substances that you don't know what they are. Sometimes basically people add substances that are actually added to mark the explosive. That's what we call tagant. The word tagant comes from the English word tag. Basically, it's just the tag you put like the little piece of paper with a cord that you actually write something, this is whatever, and then you put it, and that is funny, that is actually the original one. That's basically, that was actually hanging from the original explosives, and then you will see a little bit of history in a minute. But yes, some others basically are, not very well known what, but then that's again, those are the companies basically add those stabilizers, they add other substances that sometimes they don't disclose because, So, as we said before, the explosives basically are the main instrument for terrorism. I mean, it's not all bad when you talk about explosives. If you look at the way we use explosive to actually mine. We use explosive to actually open ways for our roads. I mean, it's when you're using explosive for the wrong reasons, when you're actually making or creating a massive problem, and then you're actually doing something illegal. And then for that point, that's where you need the use of tagans. And then that is actually the presence of these substances, these additives, that the only mission is identifying the explosive is to protect the public and to protect the governments, to facilitate the identification of the explosive. So, and that is actually why these days, basically, there will be tagans in many of the explosives that we are using. Sometimes it's known, sometimes it's not. I mean, obviously, governments and militaries are going to actually hide them and not disclose them for obvious reasons. But yeah, as I said, the word tagan comes from the little tag that you would basically hand from the explosive. And that was basically in 1971 when the US Organized Crime Control Unit, they actually require all the commercial and military explosives to be tagged. And that was just a label. I mean, you can imagine when someone basically steals explosive, you basically detach the label, then bye-bye, you don't have identification. So obviously that was pretty obvious that it wasn't going to be very efficient. So actually, in 1978, there were people basically thinking, what we can add to an explosive to identify the explosive before and after the explosion. And that is basically why they started thinking about it, and then they actually looked for non-reactive, and that is absolutely key. Wherever you add to the explosive cannot actually make it unsafe. And then we will see some examples later where some of the tagans that are in experimentation, they were basically discarded because they may actually make the explosive more sensitive. So, but yeah, in 1980, the Congressional Office of Technology Assessment basically made a report, the tagans in explosive, and then there was like a set of criteria that you have to follow in order to actually have a tagant. And then they were basically before basically pre-blast and post-blast. So actually you can actually look at both. So actually, when we talk about tagans, we have what we call identification tagans, and they are basically thought to be recovered after the blast. And then you have detection tagans that they are basically used basically for recognition pre-blast. So what are the key factors in one or the other? So for example, for the identification, and remember, identification implies post-blast, after the explosion, they need to basically contain the information of the legal holder. So basically, you go after an explosion, you recover the tag, and you can identify the manufacturers. You basically have to be traceable through commercial channels. You need to produce with that tag and a serial number. And important, must survive the detonation. Otherwise, basically, you have something that's useless. So, and then the other type is basically pre-blast, is detection. And then you can add additives, you can add substances, but then one of the things is they cannot occur naturally, or the background levels, and then the background levels of that tagant, basically the background levels of the instruments are not interfered with. So actually you can identify the tagant, but then you cannot interfere with the identification of the explosive. Usually, I mean, and that applies for those that actually release in vapor. Basically, that has to be a long-term release, 5 to 10 years. Why? Because someone could actually still explosive today, but they're not going to use it till basically 5, 10 years time. Usually, you will find that when there is a war anywhere in the world, there will be an illegal trade of explosives because they basically get lost. Militaries basically don't account for explosive when they are fighting each other. And then basically people could actually get explosives now that may use in 15 years. So actually the tagant needs to be able to still detect or identify that explosive. They need to be detectable at PPT level, so basically very, very low concentration. The vapor should not absorb in luggage items because then it's basically you're going to contaminate those items and then produce false positives. They need to be thermally and chemically stable. They actually they need to actually have a very easy way to detect the vapors. So actually needs to be identifiable by usual traditional methods of analysis. And then they are not degrading when packaged, and then they have to be safely manufactured and they can be safely stored. So there are many, many different requirements for both identification and detection tagans. So I'm going to give you some examples of identification tagans. So the typical one is basically 3M, the company 3M, you know them. They fabricate a micro tagant. It's basically layer plastic, and then they have different colors and one magnetic layer. So the idea is basically it needs to be recoverable after the explosion. You're not going to be looking for little particles. You get a big magnet and then you recover them. And then when you recover them, you look at the different bands and it's like a color coding. And then the color coding, the different color codings, you have different combinations, and that's going to give you the manufacturer, the batch, and the information that they have to store. Usually you add these between 0.025 to 0.1% of the weight of the explosive. And then because it's plastic, it doesn't get destroyed easily, and then you can recover them easily. And then because it's plastic, it's inert, it's not going to affect the stability of the explosive, so that's important. Then the other one, the other example of identification tagant is the Explode Tracer by Axalta. And then you basically can see that is actually a combination of a pigment and a metal. And then that combination of colors and the combination of the different pigments and metals provide with the code. So actually you're going to have codes that are based on concentrations and the combination of different pigments and metals. So basically you're going to see that you meet all the previous requirements I was telling you before. I'm not going to bore you, where basically you can read on screen. But yeah, it's actually quite usable. And then people actually mix it with explosives to actually recover them post-blast and identify the explosives. So, Then you have other types, basically the Westinghouse ceramic. So these actually are ceramic-like particles, again, very strong particles that are made of rare earths, strontium chlorophosphate, erobnium, and yttrium vanadate thulium. So actually, they are not very common elements in nature, and then that is actually why you add them. And the key thing is they are actually fluorescent at different wavelengths. So actually, you choose the wavelengths, you can actually make them fluoresce. You can actually spot in it after an explosion, then you can actually recover them, and then you can actually identify the manufacturer using those. The ones based on the Curie point is actually very interesting ones. It's actually iron oxide. You know, iron oxide is magnetic, but then when you blend it with other metal elements, such as strontium and barium, you call a compound basically called ferrites. And then they can actually, you can add a phosphor, basically a phosphorescent material. And actually, these elements or these compounds are very peculiar. They basically only display ferromagnetism. They become magnetic only at a certain temperature. And the way it works is you basically put them, you recover them from the crime scene or the explosion scene, put them in a chamber, then you increase the temperature till you actually get that Curie point temperature. And then it's basically, then you can actually see when they become magnetic. So again, there are different types. So detection tagans. Detection tagans basically are substances, as we said, that are usually added to identify the explosive before the explosion. So you will see when that happens. I mean, an example is what I told you before. If you actually are lucky enough to basically get the explosive device intact. So basically, for some reason, the detonator fails, the people basically, they don't connect the cables well. For some reason, basically, the explosive doesn't go off. And then you can actually get your hands on the explosive. So yeah, you can actually identify who's actually manufactured. So there are different types. The most typical ones are the vapors, but then I'm going to go through some that actually are approaches that are not usable. Some of them are usable. So the first one is the radioisotopes. That's the one. I mean, you can imagine that very quickly. I mean, you basically are going to add a radioactive material to your explosive. So actually, you can go with a Geiger counter. You can actually say, okay, well, this is actually explosive. There's an explosive here. What is the problem? The problem is, well, we have two main problems. First, you're adding a radioactive source to something. And then when you have people working with the explosives very frequently, they are going to be exposed to a level of radiation. It might be low level, but when you have low level very frequently, that's not ideal. And the second one is what we talked about, sensitive, basically making the explosive sensitive. Why? Because you're going to add a substance that is going to emit radiation. Radiation is energy. Energy could actually act in a way that could activate some of the molecules around the isotope and then make it explode by accident. So actually, it's quite unlikely, but there is a potential hazard by adding radioisotopes. So then the other one is the electromagnetic taggant. That was the third type that I told you. So electromagnetic taggants are very clear. It's basically, they are not going to be actually added to the explosive itself. They are going to be added to the detonator. So they are going to be like a small electronic circuit that is going to be emitting a radio frequency. So actually, that is going to actually identify where the explosive is. I mean, the thing is, if the terrorists or the people using it illegally, they're going to know that you are tagging that system somehow. They can actually wrap it in metal foil. They can create a Faraday cage. And you know, the Faraday cage basically stops all the radiations from going out. I mean, we do it with the mobile phones. Basically, if you put it in one of these pouches that actually eliminate the radiations that go in and out of the mobile, basically you eliminate the communications between the mobile and the rest of the world. So you can do the same. So actually, terrorists could actually make the explosive non-permeable to electromagnetic radiation. So actually, nobody would be able to identify. So that's one of the flaws. And again, it's and that the other is more economical because obviously adding you basically produce many detonating codes. If you have to add a little bit of electronic circuit, that's going to increase the cost, and then people don't want to spend money if they can avoid it. So actually, the most typical ones that you actually can find is actually the vapor ones. Here, basically, you have different examples, and actually, this didn't come from the military. This came from the International Civil Aviation Organization because they were like worried that the terrorists could actually plant bombs in planes. They basically decided to actually add it so they could identify luggage with these explosives. So, I mean, you have many that are more usable or less usable. I'm going to concentrate in the one that actually is more typical, is DNMB. And DNMB is actually 2,3-dimethyl 2,3-dinitrobutane. And basically what you do is you add it to your explosive, and that's going to actually release a little bit of vapor. It's going to actually make it more identifiable. And why DNMB is the most common? Because the one you actually, this is the one you use to C4 explosives. C4 explosives is the most common explosives, the one that you see in the movies, that where you actually put the explosive charges, and the military are using it all the time. So actually, the good thing as well is DNMB is chemically inert. It's not going to favor any reaction, any interaction with explosives, not going to detonate it by accident. And then having a low vapor pressure is still basically higher than the vapor pressure you have from the explosive. So actually, you can identify it faster than you would identify the explosive. But the other thing is considerably lower toxicity. I mean, it's not free of toxicity because, I mean, yeah, not many substances are not absolutely inert, but then this one basically is not too toxic. So yeah, so I mean, especially when you compare it to nitrotoluene, that's actually carcinogenic. So yeah, it's actually good as well because the permeability of the molecule through materials is actually quite good. Because again, if you have a tagant and the tagant you have like the bag, or where you, and then the molecule doesn't go through the material, it's not permeable, then you cannot detect it. Then you're basically defeating the objective. But actually, it's not going to be absorbed by polyester, cotton, wool, basically typical clothing that basically suicide bombers could actually utilize, or when you put it in luggage, you could actually conceal the vapor. So usually DNMB, if you remember, the other property of antagon is that they need to be able to be detectable by usual or common means. So actually, you can see there are many analytical techniques that you can utilize to actually identify DNMB. So fluorescence, GCMS, UVBs, FTIR, I mean, many. So actually, it's it's actually important that you learn, or people learn, how to detect DNMB fast and accurately, because actually that could prevent many attacks, especially if people are using military type explosives that they have stolen from a military base or so. So now basically I'm going to go very quickly through the way we actually do things in the UK. So basically, I mean, every country has their own military or civil institution that are dealing with the analysis and basically detection of explosives. So in the UK, basically, is the Defense Science and Technology Lab, basically DSTL. They have a unit. That unit is a forensic explosive lab. It's basically FEL. And they are the responsible for the analysis identification of the explosive material. And the FEL has been in existence since 1870s in different forms, basically forming part of different bodies. But you basically get the FEL there every time there is an explosive alarm, and they need actually their presence. So give you a couple of examples. I mean, just people basically playing with explosives. I mean, the typical ones that people play is peroxide explosives. Again, very silly thing to do. Every year, there are many people dying and basically losing hands and losing limbs because they are trying to manufacture explosives. Sometimes teenagers that they want to create a little explosion, and then they don't realize how dangerous these things are. Sometimes basically they are not teenagers, they are basically people with bad intentions, and then obviously they want to actually create damage and more serious damage. So in this case, basically there was these people that during a raid in a property, basically they found some small crystals, and they found basically that the crystals were in the respirator. They basically found the crystals everywhere, and then when they analyzed the crystals, basically they realized that they were in front of basically HMTD, basically hexamethylene triperoxide diamine. And then obviously it was everywhere because they basically go everywhere. And then you can see the jacket, shirt, belt, watch, basically everywhere. And then they found small initiators, and they were basically trying to connect it. So actually they were trying to prepare a bomb. So actually the guy was jailed and then sentenced for 2 years. So another example, and sadly is basically very, very well known, is the 7/7 bombings. So actually they were basically the Islamic attack on London, and they killed basically 52 people. The FEL attended the scene, and then they recovered some unexploded artifacts. So actually that was a very, very lucky finding, because when you find something that hasn't exploded and you have everything like detonators, you have the explosive, you can actually use it to frame people later and actually to take them to court, because then you're going to tell them, look, we know it's you because we basically done the forensic analysis, and the fingerprint of your explosives actually match the fingerprints or residues we found in your clothing or any items that belongs to you. So actually, the important thing is they can be used for intelligence. So after the attack, 5 days later, basically, the police raided a property in Leeds. Leeds and London are not far, basically are not close, sorry. They are actually far away. And then basically they were the place where they suspected the bombs hadn't been manufactured. And they actually found evidence, buckets containing some substances, basically HMTD. And actually they were basically playing with pepper and hydrogen peroxide explosives. Again, they were trying to implement easy to make explosives. Again, not very basically, yeah, safe to play. But then again, and just to give you an example, the Barcelona attack, there were basically an explosion. They basically killed many people. But then when the police was trying to raid the property where the terrorists were, they basically, they blow themselves. And the police actually at that point actually had evidence that another previous explosion had been caused by TATP, and because they simply didn't actually manufacture that safely. And as I said, when you are trying to manufacture these things in a way that is actually homemade, you're going to have loads of impurities, and then that's going to create massive problems and probably kill yourself. So again, it's the typical thing that you do not try to do this at home. You do not try to do it unless you're working for the specialist people, or you need to do it for a specific purpose in a lab under supervision. So basically, again, that's what we did. I mean, we fabricated explosives. We had basically one of our specialists, Peter Perini, he works for a company called Extreme Performance, and then they basically have access to military grade detonators. Basically, we had very pure substances. We got basically chemicals from the lab. We produced a very, very effective explosive, and then we detonated it. You saw that explosion. And what we did? But we recovered the fragments, and then when we recovered the fragments, we were analyzing for residues. Unfortunately, basically, that would have been great for a post-blast type of marker. But what we did as well was the tagging, and that's going to be, that's the question there, is chemometry an alternative to tagging? I mean, chemometry is basically used in multivariate analysis. It's actually using lots of variables to actually identify a fingerprint of any substance. So we tried to actually use a pre-blast taggant, but then we were looking for the composition of the fuel that we were using to produce the bomb. So actually what we did is we fabricated different explosives with different properties. So we went through the different petrol stations around the city, and then we actually got different small amounts of different petrol samples and diesel samples, and we actually created the bombs. But then we did what you would do if you recover an unexploded explosive. We actually got extracting the fuel. In this case, the petrol sample. We follow, I mean, the paper basically explains everything. I'm not going to explain everything. But yeah, we extracted it. We analyzed it using FTIR and gas chromatography mass spectrometry. We selected a number of markers. And then based on that, we did our chemometric analysis. And we could actually separate the different petrol stations, Shell, Esso, BP. So actually, why is this important? Well, imagine you get the explosive, it hasn't exploded. Usually terrorists they prepare the bomb, they try to use it as fast as they can because it's not safe to keep. So actually, if you know that the bomb has been prepared with BP, that petrol, you go to all the BPs that you have in a certain perimeter, and then you go to the owner, say, can I have your CCTV camera recordings in the last week? And then you can see who's been buying cans, individual cans, because that's odd. I mean, if you're putting petrol in your car, yeah, but if you actually go and buy a can, like in a jerry can, that usually, yeah, people say, oh yeah, I ran out of petrol, I need to fill up the tank in my car. Yes, but maybe not. And that's where intelligence can be very important, because then you can actually look at the picture of the person, run it through face recognition, again, using chemometry, basically neural networks, and then you can identify those people, whether they are terrorists or not. So the other thing we've done very recently, and this is actually, you can see, is 5th of August, 2022, basically 3 days ago, we got a paper accepted, and that's actually the effect of metal catalysis in the electrochemical oxidation of petrol. So actually, yeah, identification of pre-blast samples is very important, but then you need a GCMS and you need an FTIR. Some of the FTIR are portable, but if you want a machine that can actually do the job very fast and very quick in the spot, electrochemistry is brilliant for that. Why? Because you can have a small potential stat, you can actually run a portable system, you can do the analysis basically in a little van in the crime scene or just outside the place where you actually got the explosive, and then you can run your analysis. And then, as you can say, you can actually use electrochemistry to identify Shell, Gulf, Esso, Tesco, Sainsbury's, BP, different brands of different fuels used to produce explosives. In this case, it's a little bit trickier because we had to play with a very special electrodes. Platinum is an electrocatalytic electrode. And then we were working with adding some metals to the mixture. And then, for example, iron, I'm producing a second, basically a combination of electrochemical oxidation that has been aided by metal catalysis. But even doing that, basically, we got a signal that was quite unique for the brand. And then we, using chemometrics, again, we could separate the different brands. So our, basically, Dr. Prael, basically, she got her PhD, so she graduated with honors. We are basically still publishing papers from her PhD. So actually, and then you have a picture of her basically in her military uniform. So yes, she came back to Bangkok. We keep in contact, and then she's basically, we keep working together. So conclusions of my talk. We need to add tagans to be able to trace explosive before or after the blast. we basically can use taggants in civilian applications, because some people could actually steal those explosives, and then you need to know where. But then also in military applications, you're going to actually have taggants added. But then some of the taggants are secret, and then you don't know what they are, what compounds you have there that actually only military knows. Many substances can be used as taggants, as you could see in the presentation. But yeah, there are basically effective detection methods. That's where we can add chemometric. So actually, chemometric analysis could be like an artificial mathematical taggant that you can actually use knowing the composition of your explosive. But there are still basically more research done in this area. So we can identify explosives to prevent anybody from misusing them. So, muito obrigado. And if you have any questions, I'm here to actually answer any questions you may have. Thank you very much. Sherlan, you're muted. You're muted.
I'm having problem with my microphone and camera, but it's okay now. Well, thank you, Professor Jose, for your presentation. Your experience in forensics is amazing to me. I like to hear you talking about this kind of object. We have here some questions from our audience. I'm gonna remove your presentation now, so we can talk. We can see you and me.
Yeah.
We have some questions about your doubts and comments about the presentation. I'm gonna show some of them. Sunny asked if is there any special.
Oh yeah, definitely. You shouldn't be working. Oh, sorry.
Okay.
I jumped in.
No problem. Go on.
Yeah, special training basically. Even if you're a graduate student, you shouldn't be working with explosives. That is the main thing. That's the main. You should only be working with explosives if you're working with people who have been authorized by the military or the police to actually work with explosives. Because I mean, you see, I'm allowed to work with up to 100 grams of explosives according to British law, but that depends on the country. I don't know the legislation in Brazil, but if you actually, some countries are very strict. Even having 1 gram or 2 grams of explosives could be enough to actually get you in jail. A first aid course, basically, if you chop your finger, basically, it's not going to be of much use. Or if you killed yourself, basically, nobody's going to resuscitate with a first aid course. So the best thing to do is not to play with explosives. If you want to play with explosives, join a unit that actually works with explosives. Join the military or work with police forces to actually do that job. But then I wouldn't actually. You don't get a special training. Basically, special training is when you actually join the forensic labs, I'm afraid. So,
and in this sense, how someone like me, for example, could begin to make research or to do research on forensics with some restricted materials, like or require some special training to do this?
I mean, you can do research in explosives very easily. I mean, because you can buy explosives in a very safe way. So you know that basically when we're talking about analytical explosives or analytical standards for explosives, sometimes you have enough. You have 1,000 ppms. And then, for example, Ceruleum, they sell small ampules of 1 milliliter in acetonitrile, and you have 1,000 ppms of HMX, RDX. So that is the way you could actually do safe research with explosives. Again, I would refer to the Brazilian law before you start actually manufacturing explosives. So, for example, when we manufactured the ATP or we manufactured info, I knew the British law. I know that for research and analysis, I'm allowed to actually produce 100 grams. But then, you see, to get detonators or the detonators you saw on the screen, we needed military grade, and we are not allowed to use military grade. But Peter, he's trained because he's in a company that actually sell these things, and the government is actually guaranteed that he's actually safe to work with. So again, I would talk to the police. If you want to do small research with analytical standards, you could do. I mean, that is actually
but
easy.
but it would not be rather far from the reality to perform such a kind of
No, I mean,
research.
so if you basically get analytical standard 1,000 ppms and you're looking for a method to detect traces of explosives in a matrix, that's actually, you could do it. Or for example, if you look at electrochemical detection of explosives with 30 ppms, you see when we did the paper, we produced a paper, a molecular imprinted polymer, a very selective and sensitive sensor for TATP. We're basically able to detect TATP at 20 parts per billion. So that was actually competing with the GCMS and the LCMS. And you see, we manufactured TATP because we wanted to actually follow the whole thing, but we manufactured 1 gram because we were basically we didn't want to risk it. You see, to actually produce the calibration curves, we were using standard commercial standards. So actually, yes, you can do that. Yeah.
Yeah.
I can see
good to listen to
this. Commercial.
We have more questions. We have one from Professor Falston, which is in UK, in Bristol right now, for his postdoc stay. Hello, Professor Jose. First, congratulations on the presentation. I'd like to know which tests, characterizations are done to verify the influence of target on explosive performance.
So basically, I'm assuming you're asking, how do we know the targets are going to be safe to add to an explosive? I'm assuming that's the question. So actually, I mean, as I said before you add a target to an explosive, you have to go through many tests. You basically, one is time test, where you actually leave it there. You actually basically change the different conditions where the explosive could be stored or it could be transported, just to make sure that the target didn't actually attack or basically oxidize or influence chemically that explosive. I mean, there are many different methodologies you could actually follow. I mean, there are some standard procedures. Basically, I'm not familiar with every of them. Stability tests are one of the typical ones. But yeah, I wouldn't be able to tell you like a long list of sorry.
There's another question from Frau Falston. What characteristics make a good target?
So if you go to my presentation, I can remember then you have the 2 different targets, and then what are the characteristics you need to have for each of the targets. So you will see that they need to be recoverable. For those actually post-blast, they need to be recoverable after the explosion. They need to be able to be tracked to basically identify the serial number. For those actually pre-blast, they need to be stable. They don't need to actually influence the explosive, so they make them sensitive. So if you have access, I mean, you can. I've been told this is recorded, so you can actually rewind.
Yes, it's recorded, gonna be hosted on our
I hope I didn't say many silly things. So.
There is another question from Sunny. There are measures to reduce the illegal use of explosives.
Oh, that's a very good question.
The explosive industry should follow.
Yes. So to be honest, the measures is basically for the manufacturers to actually, or the users to actually keep them safe. So actually, when you are storing explosives, you shouldn't basically make it obvious. You should have basically a very secure access to those facilities. Because again, mining operators basically have the quarry. The quarry basically contains usually like a secure area where you have your explosive. That should be only restricted access to certain people. And the most safety you implement in the access to explosives, then the less chances robbers or basically or terrorists are going to have to actually steal your explosives. I mean, and then more important than the explosive as well is the detonator. I mean, because sometimes manufacturing alpha is fairly simple, but getting a detonator that's powerful enough to actually detonate ANFO, yeah, that's not that accessible. So you see, TATP is very easy to manufacture. You can actually detonate TATP with a small oh, my brain, sorry, it's late. But yeah, like fireworks, sorry. But yeah, or any intense source of heat or electricity. But yeah, again, that makes them so unstable. So that's why, again, the best, come back to what I was saying, is the best way to do it is try to avoid that. And again, don't play with
it's a good advice.
Oh, you're laughing, Sheldon. When I did my chemistry degree, we were in the third year or second year in organic chemistry. My lectures basically refused to give us the gunpowder recipe because weeks before, someone basically blew their hands in Madrid in the School of Chemistry.
Really?
Yeah.
Oh.
So yeah, it's people do stupid things.
Yeah. Well, moving on. How much does the detectability of vapor taggants, such as GNB, change with time?
So that's a good, because obviously you're going to add the concentration. We're talking about 0.1%. So with time, basically that vapor is going to go. So the longer the time, the least detectable the taggant is going to be. So, and that's what I was saying. Some people basically get the explosives and they don't use it in 20 years or 15 years. I mean, there are people probably still storing explosives from the former USSR, where basically they were so open access to actually get everything you wanted. And then they explosives are not going to go off. They are not going to, I mean, if they are securely stored and then preserved well, they can basically be usable hundreds of years afterwards. I mean, you have bombs from the First World War that actually explode, and grenades. I mean, it's if they actually contain, they are dangerous for decades.
100 years.
Yeah, I mean that's why, in a sense. But yeah, the taggant is not going to be there for that long, because the taggant by nature is going to evaporate to favor the detection of the explosive. So eventually, you're going to have less and less and less concentration. So it's going to be more difficult to detect.
Okay, we have some comments on your presentation. Thank you, Marilia, for your question. We have a comment from Sandy. Thank you for excellent talk, Professor Jose. One comment for Karen Weber. Congrats on a very nice presentation, Jose. And a final question also from Marilia. May I ask you to talk a bit about the sampling? Is it expected for the proportional concentration of different analytes to change with distance? Or are they more or less homogeneous? Matthews.
Yes.
Matthews via Marilia.
Yes, okay. Especially you have a courier to ask for a question. But yeah, I'm assuming you're asking that because you saw the test plates that we had in our explosions. Yes. So yes, that changes with. I mean, when we did it, we in conditions where the blast basically, even where the charge was, if you basically manufacture charge and then for some reason it's not homogeneous and then explodes in a certain direction, you're going to have that some plates are going to be more contaminated and the other plates are not going to be that contaminated. So basically the concentration, it could be actually different depending on the weather conditions, depending on the wind direction, depending on how well you manufacture your explosive to be in a spherical blast rather than in a directed blast towards one of the plates. So in our case, we did it actually well. So we were basically good bombers, and then we did a very good bomb, and then it went basically everywhere. And actually, so our system was actually quite well symmetrical. But then obviously we had Peter's a specialist in bomb manufacturing and explosives. So actually, he could tell us. I mean, because we don't study those things. I mean, he told us how to do it. So.
Okay. We'd like to end our talk, our chat about this incredible and amazing subject is explosives and explosive targets with Professor Gonzalez-Rodriguez. I'd like to thank you again for your participation in our first seminar of the semester in this event celebrating the anniversary of the program. Thank you, Dr. Jose. Thank you for your brilliant presentation. And we hope we'll meet you again.
Definitely.
Another opportunity. Thank you, Dr. José. Thank you. E eu gostaria de agradecer a todos que estão presentes aqui virtualmente e presencialmente aí no auditório, né, da nossa universidade, e dizer que nós estamos encerrando por aqui. Tá, pessoal? Até mais e um grande abraço. Bye, bye. Obrigado, José, e um grande abraço. Tchau, tchau.
Tchau.